Okay, everybody, welcome back to another video lesson on solutions. This video lesson, what I'm going to focus on is the solution or factors that are going to affect your solution formation. So let me see where I have that. Here we go. So factors affecting solubility is what we're looking at. Now, what we've seen before, or what we've talked about, is that there's those attraction forces that are going to be in the solute and solvent particles. Well, the solubility is going to increase when those attractions between the solvent and the solute become more magnified or more similar to each other, I guess is a better way of saying it, that they're more alike each other. So the more alike those intermolecular forces are, the more the particles of the solute and the solvent just kind of blend together as if they can't tell the difference between what they're attracting, right? So if water is highly polar and sodium chloride is highly polar, well, water can't distinguish between the polarity of the ions and the polarity of the water itself, so therefore they just kind of all mingle and merge together, and entropy has the overriding effect. Alright, so there's three factors that we're going to look at. One is structural effects. That tends to be the hardest. Pressure effects, not too bad. Temperature effects, most of you already know. So let's focus most of our attention on structural effects. This is where you're going to really want to be able to draw Lewis structures and look for those hydrogen bonding and dipole-dipole moments in your structures. Now, we said that based on entropy, if that were the only case, then everything should mix together. You should blend right into the air. You should, if you bumped into a wall, you should mix right into it. But the reason that doesn't happen is because of the structure of the particles that make up you and the wall in the air. So the structure of those particles, there's going to be more attraction forces inside of your body than there are to the air or to the wall. And that's a good thing. So there's a disorder has a huge effect when the forces are closer together. So if our forces are closer together in attraction forces, then we would say that you would start to dissolve, and disorder or entropy would have the overriding effect. And that's why we get to that like dissolves like. So strong intermolecular forces between the solute solvent keep it together from going into there, and it tends to have a low solubility. Okay, so let's take a look at our first set of data. What we have here are some gases. We have nitrogen, carbon monoxide, oxygen, argon, and krypton. And what we're looking at is the molarity. Now, molarity is indicating the concentration, the solution. And as we go down, we can see that the solubility is increasing. So as we go down this list, we have a higher and higher solubility. So why is it that nitrogen has a low solubility where the krypton has a high solubility? Well, if we look at these substances, excluding this one, I don't know why carbon monoxide is in here, but we're just going to ignore that one for now because that shouldn't be there. All right, so you've got nitrogen, oxygen, argon, and krypton. The reason I'm taking that one out is that that's a dipole substance. We don't want to look at that. We want to look at all nonpolar substances. So nitrogen, oxygen, argon, and krypton all have nonpolar attraction forces. As I go down that list, notice that the molar mass increases. Now, as the molar mass increases, what happens is I have more protons and more electrons in my substance. So even though krypton is an element and nitrogen is a molecule, and there's two of them, I still have more electrons in the krypton. And remember, since they're all London dispersion forces, since these are all London dispersion attraction forces in these four particles, then the stronger London dispersion force is going to have the highest solubility. So why does the London dispersion force for krypton the largest? Well, it's not because of the molar mass. The molar mass is our way of indicating that. The reason is because krypton has more electrons, and therefore it can polarize the molecule longer. So if we're trying to dissolve these gases into water, the more like water, and I probably should have said that in the beginning, that we're trying to dissolve these in water. And by the way, that's always the default setting. If you're not sure and it doesn't specifically say, always assume that water is your solvent. Okay, and water has hydrogen bonding, so we want something that is more and more like hydrogen bonding. Well, London dispersion is kind of the opposite. It's the weakest of those forces. So London dispersion forces aren't going to dissolve readily into water. But if that London dispersion force gets stronger and stronger and stronger, it becomes more and more like a strong hydrogen bonding, right? So as we go down, we see that the solubility increases. Now it's still very low solubility. Not a lot of krypton dissolves in the water, but that's the way it is. Now, oxygen, obviously, is a low solubility too, but that's enough for fish to breathe, right? The fish breathe the oxygen that's in the water. So we can see that gases do dissolve in water. All right. Let's move on to hydrocarbons. These tend to be the more difficult ones for students. Don't overthink this one. A lot of students overthink this one. So here we go. First of all, relatively short, pure hydrocarbons do not dissolve in water. I'm going to draw those down here. Don't look at this chart yet. So if I have something like methane, which is CH4, CH4 is a very small hydrocarbon. It has a very low solubility in water. It will really not dissolve in water much at all, because of the fact that it's nonpolar. Since this is nonpolar, it has London dispersion force, and it has a very weak London dispersion force. And since the London dispersion force is very weak in the methane, there's not much attraction for methane in water. So therefore, very low to no solubility of methane in water. Okay. Now, as I make that chain bigger, I then move to what's called ethane. Okay, so ethane would be C2H6. Now for C2H6, it's still nonpolar, but just like we said for the last slide, the London dispersion force is getting a little stronger. So the solubility is going to start to go up. So it's still low and it's almost not very soluble at all, but as that chain gets bigger, let's add another hydrocarbon here, and let's just say we do a hydrocarbon that's really, really long, okay, and then put the C2CH3 here. Well, that very long one is going to have a high solubility. Okay, so the key here is that the longer the chain, the higher the solubility of a pure hydrocarbon. What I mean by pure hydrocarbon is that it's all carbons and hydrogens in there. Nothing else is added in there. Okay, so we've got methane, so low solubility to high solubility. Okay, as that London dispersion force gets greater and greater as we go down these particles. Okay, because of the polarization due to the high number of electrons. I know I keep saying that, but you know, a lot of students get that backwards. A lot of students want to say, oh, because it has a higher molar mass. Don't do that. Okay, now let's see what happens if we take off one of these groups. If we take off that methane group and we add an OH on here. Now you should recognize right away by adding this OH on here, one thing we do is we create what are called alcohols. Alcohols, we'll talk about the naming of these a little bit later, so don't worry about that right now because they'll give you the names at this point. But this is methanol. Methanol is just a hydrocarbon. We take off one of the hydrogens and we put on an OH group. That OH group is now, I'm not going to draw the hydrogens, but you know it will now have strong hydrogen bonding at this region. Now because the molecule is really small, there's not much of the nonpolar part, this can attach to the water, water attracts to this part, and it readily dissolves in water. It will completely dissolve. That's what this is, an infinite solubility. You can mix these three together infinitely within each other because the molecule is still relatively small. Still relatively small. Now we're starting to get larger, so our solubility is starting to go down. We're starting to see, now here's the opposite, right? Over here I said that as the chain got larger, solubility got larger, right? So it's the longer the chain, higher the solubility. Over here, as the chain gets longer, our solubility is going to start to go down. We're going to have a decrease in solubility. What's making this dissolve in water? It's the OH, that alcohol group that's on the hydrocarbon. Now, because this is only one hydrocarbon on here, one hydroxyl group, doesn't create a lot of hydrogen bonding, this chain overrides that little bit of hydrogen bonding and makes it very insoluble. Okay, so it's all about the structure. Now, they're not going to ask you what's the cutoff. I know a lot of students say, well, wait a minute, well, when is this? Because, again, if I make this chain long enough, isn't the London dispersion force going to start to increase and cause solubility to go back up, right? Don't worry about that. What you want to do is just compare the ones they give you. If they give you this one and they give you this one, which one has a higher solubility? The smaller one. If they give you, ethane and they give you, let's just say, well, I guess we'd just say ethanol. And they say, why is ethanol soluble in water? Well, this one isn't. It's because of that OH group. Okay. Now, let's complicate things a little bit more. All right, let's take a look at glucose. Glucose is a form of sugar. Now with glucose, again, they're not going to expect you to know this structural formula. This is a pretty complex structure. These are carbons at these points along here. They don't write the carbons in, but these are all carbons at these intersections. Okay, and this is like coming out at you, and this is going back. It's in line, going back into the board, and this one is in line with the board. Don't worry about that stuff. What you want to focus on is this. Take a look at glucose. Glucose has a lot of these OH groups. It's a long hydrocarbon, that ring structure, but take a look at the fact that there's a lot of these O's and OH's on here. Even this oxygen, even though it's not a hydrogen bonding, it still has those lone pairs of electrons on it. It's going to attract some water. So H2O will be attracted there, it's going to be attracted here, it's going to be attracted here, more water is going to be attracted here. Now even though this chain is long, it has a lot of OH groups on there. So here's the problem, is that I can have really long hydrocarbons, but if I put more of these OH groups on here, it's going to increase the solubility. So you really have to look at the structures in detail and say, well, which one has the most hydroxide, or what are called hydroxyl groups. It's called a hydroxyl. Okay, called a hydroxyl group, and it just produces hydrogen bonding within the two molecules of it. Okay, another example. So sugars. Let me just finish with the sugar. All sugars, sucrose, fructose, glucose, and any other sugars that you have are all going to relatively dissolve because they have a large number of hydroxyl groups on there, which increase the hydrogen bonding. Now let's take a look at vitamins. There's two types of vitamins that are out there. There's vitamins that are that will dissolve in water, and others that will not dissolve in water. Ones are fat soluble, others are water soluble. If we take a look at vitamin A, if we look at the structural formula of vitamin A, look at this, a lot of hydrocarbons, big long chain of hydrocarbons with just this little itty bitty hydroxide group on here. Would we expect this to dissolve very much in water? No, it shouldn't, because it has a large, long long structure that's nonpolar. It only has this little portion here that has that partial negative and partial positive. So vitamin A is not very water soluble, and that's good for you, because what happens is that it's actually going to dissolve in your fat, because your fat is also nonpolar. And what that means is that your body can store up vitamin A. Vitamin A doesn't have to be replenished as much as something like vitamin C. Take a look at vitamin C. For vitamin C, we've got an OH group here, we've got an OH group here, an OH group here, and don't forget the lone pairs of electrons on this also attract the water as well. Even though it's not hydrogen bonding, it's still going to be attracted, and anything with those lone pairs of electrons on the outside are going to do that. And you also have a negative charge here. So all of this stuff contributes to a high solubility of the vitamin C. And that means that's what's called hydrophilic. Hydrophilic means that it's water-loving. Hydrophobic means it's water-fearing. Obviously, these things don't fear or have any love for the water. It just means it's attracted to the water. Now, with vitamin C, because it's soluble in water, that makes it kind of a dangerous vitamin, because it will dissolve in the water in your body, and it will be passed out through your body in your urine. And what that means is that you have to keep replenishing your vitamin C on a daily basis, because of the fact that it's water soluble, and you have to replace it daily. Here, this vitamin A can be stored for long periods of time and can be used over and over again. So vitamins B and C are hydrophilic, meaning that they're water soluble, so you need to replenish them over and over again. Vitamins A, D, and E, and K are hydrophobic, and therefore they don't need to be replenished as much. Okay, so you can see an example of how the structure, and not only the structure, but the components that are in the structure have an effect. Alright, so that would be your structural effects. I know it's kind of a little confusing, but you guys are smart and you'll figure it out, and we'll kind of work on it together over the next couple days. Alright, last thing is on pressure effects. Pretty simple. This one is going to just deal with the solubility of gases. So when a gas is dissolved in water, the increase in pressure on the system increases the solubility. Think about a can of pop. Simply think of a can of pop. The can of pop is closed, it's under high pressure, and your carbonation stays in it. As soon as you crack open the pop, and it makes that popping sound and it releases the gas, then the gases inside are going to come out. So you'll have that water, you got the gas particles in here. Well, if there's pressure pushing down on this, then those particles stay in. But as soon as that pressure is removed, as soon as we take away that pressure, we then have the particles can now start to go into the gas phase. So we can now start to see these particles can now go off into the gas phase if there is no pressure here. And that's pretty much it. Liquids and solids are not really affected, and this means liquids and solids dissolved into the water. That's where not just liquids and solids themselves, but liquids and solids dissolved into the solution. They have no measurable effect when you change pressure, just the gases. So as the pressure increases, solubility goes up. Okay. Then the last part is temperature effects, and most of you should know this from Honors Chem, just an intuitive idea as well. I already talked about this equation back when I talked about sodium chloride dissolving, but take a look at this. This is temperature, and this is your solubility. Pay attention to the key here in case they ask you questions about this. This is the grams of salt dissolved in 100 grams of water as your solvent. So as I increase temperature, notice the potassium chlorate increases, the potassium dichromate increases, potassium nitrate, lead nitrate. Most of these substances increase with solubility. The cerium sulfate, notice it does the opposite. Okay, we're not going to get into the reasons why that does that, but it just has to do with going back to look at this equation and whether the entropy increases and all that other stuff. But anyway, most solids increase solubility with increasing temperature. Obviously, sodium chloride doesn't change that much, whereas potassium nitrate increases drastically. It's a huge slope. Okay, so you should know this, right? If you heat up water, you can dissolve more salt or more sugar into your water. Now, the last one is gases, and that would be gases dissolved in water. As you increase the temperature, I don't have a chart for this one, but the gas will decrease as temperature goes up. Because if we have our gases dissolved into the water and we increase the kinetic energy by heating this up, the gas particles come together and collide more often, which creates the bubbles that then come out of solution. So overall, increasing temperature will always decrease the solubility of all gases. There's no gases that won't do that. Alright, so that pretty much ends the information for solutions. I will see you guys in class, and we'll kind of go over all this and make sure that you understand it all for your test. Thanks a lot.